Hello, I want to tell you about our new paper, A Search for Dark Matter Lines at the Galactic Center with 14 years of Fermi data. I'm Ben Safdie, and I wrote this paper together with Josh Foster, Eugen Park, Linda Shu, and Yotam Sorek. We improved the limits on decaying and annihilating dark matter to gamma ray lines using data from the Fermi Large Area Telescope taken from 2008 to 2022. We used data between 10 GeV to 2 GeV, and we selected the top 3 quartiles of data as ranked by energy dispersion because we expect our signal to be narrow in energy space. We selected data within the inner 30 degrees of the galaxy because that's where we expect our signal to peak. And we looked for both dark matter annihilation and decay, modeling the dark matter profile by NFW and contracted NFW distributions. You can see our regions of interest down here at the bottom, where we mask the galactic plane at different amounts, depending on whether we're looking for dark matter annihilation or decay, and depending on the form of the dark matter profile assumed. Here's a zoom in of our region of interest, which we divide up into 30 concentric annuli. Within each one of these rings, we stack the data to construct spectra like what you can see here, where we have the spectrum on the y-axis as a function of the energy on the x-axis. Remember, we're looking for dark matter decay into gamma ray lines, which result in narrow spectral features. So we analyze the data in a narrow energy window around the energy of interest where the line would appear. In red here, you can see our line, which is broadened out by the detector energy resolution. And within this narrow window, we model the background using a power law background model, and we adjust this energy window depending on the location of the line. We find no evidence for dark matter decay or annihilation, so we set 95% upper limits on the annihilation cross-section to photons as a function of the dark matter mass. In black here, you're seeing our limits, which are power constrained, meaning we don't let the limit go below the 1 sigma expected limit under the null hypothesis, which is what's shown in green. Our limits improve over the previous Fermi limits by incorporating more data and also using a region of interest more optimized for the signal. At very high masses, our limits are surpassed by those of the ground-based HESS telescope, as one might expect. And as I already mentioned, we find no significant excesses, no evidence in favor of the dark matter model. Our results have a number of implications. One, for example, is to the Fermi Galactic Center excess. The GCE is an excess of GeV gamma rays, first observed back in 2009. It's a continuum excess of gamma rays. Here you're seeing the spectrum of the GCE on the y-axis as a function of energy as extracted by many different groups. You can see it's a broad excess in energy space, spherically symmetric about the galactic center, and it's received a lot of attention because it could arise from dark matter annihilation, although astrophysical explanations of the excess are also possible. If you interpret the excess in the context of dark matter, you find you need a contracted NFW profile, and the excess should arise from continuum annihilation. So for example, dark matter going into BB bar, which then shower down and give you a continuum spectrum of gamma rays. And excitingly, you would need a near thermal cross-section in order to explain the GCE. One example of a dark matter model, which can explain this excess, is a Higgs portal model with a Lagrangian like what you can see here for a Majorana fermion chi. Here you can annihilate through the Higgs portal into standard model fermions. So in addition to annihilating to standard model fermions at tree level, you also, and this is rather generic, have a 1-loop contribution into 2 photons. And if you work it out, you'll see that the ratio of the loop cross-section to 2 photons versus the tree level annihilation cross-section is around 10 to the minus 3, assuming a 40 GeV dark matter mass, which is what you need in order to explain the galactic center excess. So that allows us to do the following. Here we see the total annihilation cross-section for the Higgs portal model. The red ellipses show the best fit parameter space in order to explain the galactic center excess with the tree level process. And then in black are our 95% upper limits translated into a limit on the total annihilation cross-section. And you can see that our limits constrain the Higgs portal explanation of the galactic center excess. The shaded region in gray is actually disfavored by invisible Higgs decays. So you can see that invisible Higgs decays already constrain the best fit parameter space, although those constraints are a little bit model dependent. So in summary, the Higgs portal model is constrained by the lack of gamma ray lines, and we show that similar results are also true for neutralino explanations of the galactic center excess. So in summary, we set strong constraints on dark matter annihilation, which is what I discussed, and also dark matter decay into gamma ray lines. We looked for evidence of these lines in archival Fermi data, and we didn't find any evidence for beyond the standard model physics. The monochromatic signals are typically one loop suppressed relative to the tree level processes. However, they're easier to look for versus the tree level continuum signals because we're looking for a narrow bump, which means there's less background and also, importantly, fewer confounding sources of systematic uncertainties. There are a variety of implications of our results, for example, for the galactic center axis, and also more generally in the context of a variety of decaying and annihilating dark matter models, such as neutralinos, gravitinos, and glue balls, amongst other possibilities. So thanks for listening. Please check out our paper, and please let us know if you have any questions.